we're taking a look at this data sheet here, and we need to be able to get a status that comes out of this sensor to know if the status is 0, if all these bits are 0, then we've got an OK message back from the sensor and we can use its value. If some of these bits are set, they correspond to errors and we don't want to use that value. So for example, the preheating bit here, if the sensor is still warming up, then we can't rely on that value yet. We want to throw that value away or ignore it and wait until the preheat's complete. So then that sets it back to 0 there for that bit. There are some other bits here that we really don't care about. They're more just like informational or warning bits than like hard errors. So if the measurement is less than the measurement range or over the measurement range, these are kind of like soft ranges defined by the sensor. If it happens to go outside that, the value might be a little inaccurate, but for our purposes, we don't really care. We're just using that as information. We still want to be able to capture the value there. So we've got some code. We'll go into a little tutorial around this, so we're not showing the actual project code off here, but we'll go through basically a similar example. And so we've got a status that comes into the code here. Actually, let me just recreate some of this table here. So we've got, they called it bits 7 through 0. I'm going to relabel these bits 1 through 8, and this will make sense why later on. It'll just make this a little easier to work with as we think about it. But we got a reserved bit. We'll just do the numbers. 8765. There we go. And so if everything is okay, each of these bits are 0, and we get a value of 0. So our status is equal to 0, gives us okay. If we have a status of anything else, let's return an error. All right, so now if we run this, probably no surprises here. We're going to get, if we put a 0 in there, we've got okay. If we put any other value in there, I can put 15 in there, I can put 200 in there. Now it's invalid. But the catch is these two bits, bits 2 and 3, these measurement range bits, we really don't care about them. So if we get a value of, and so I said 2 and 3, we renumbered them here, so they're 3 and 4. So if we get, oops, let's just copy this. So there's going to be 3 possibilities here we care about. Or well, we'll just start with these 2. So if we have a value of 4 or we have a value of 8, I'll get to that in a second, we still want to be okay. And if I put a 4 or an 8 in here, we're still going to get errors. So one way we could do this, the simple way, is if we guard closet, we could say when status is 0 or status is 4 or status is 8, then be okay. Oh, and we have to use the keywords. So now if we do a 0, a 4, or an 8, it's okay. It's ignoring those bits. Oops. Oh, why did that just go away? There we go. It's ignoring those bits. Otherwise, it's invalid. But working with the decimals here, it's kind of like, why did you get 4 and 8? How do you start determining what these values are? Because we're sitting over here looking at a bit field. And this doesn't seem very easy to convert into decimal. So the trick to going binary to decimal is a pretty easy one. It's use the programming calculator. This is only a half joke. Binary to decimal is not the easiest conversion. But if we say, let's just put a binary value in here, and we've got 4 zeros, a 1, and 3 zeros. And it says down here in base 10, so 8 base 10 is an 8. 8 base 16 is giving us the hex value. It also happens to be 8 in hex. And for some of the smaller numbers, you can do them in your head. For some of the larger numbers, it becomes a pain. The way to do the math on this by hand is something I'm not going to dive too deep into, because honestly, just use the calculator because you're going to be on a computer anyway. But it starts off, the first bit starts off at 1, and you do the power of 2 each time to get the next one. So if I switch the calculator back to decimal and we do 1 to the power of 2 is 1. So we start off with the first bit is 1. And then to the power of 2, why is that not working? Well, I'll just tell you the next one is 2. I don't remember why 1 to the power of 2 is not doing it. Oh, sorry, I got that backwards. The first one is bit 0. So it's actually 2 to the power of 0 is 1. That's your first bit. 2 to the power of 2, or sorry, 2 to the power of 1 is 2. So 2 is your second bit. 2 to the power of 2 is 4. And so you just keep multiplying like that. So 4, 8, 16, 32, 64, 128. And that should be 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So anytime you put one of these bytes here, or one of these bits here, it represents one of these numbers. And so use the number above it and add each of these up. So we have 1, 4. So that equals 4. If we were to do the 4 and the 8, so that becomes 8 plus 4, that's 12. So this starts working. You can kind of do this in your head for the smaller numbers. Once you get a handful of bits in here, like this type of thing, sure, you can, if you're good at mental math, I'm not, you could do that in your head. If you do it on the calculator, 128 plus 64 plus 16 plus 4 plus 1 is 213. And if we look at the bits down here on the programming calculator, 1101, 1101, 0100, 0100. So that's how you get it. That's the long form way. It's incredibly tedious to go from decimal to binary and backwards. The fast way, honestly, is to use the calculator. It's not easy to do mentally. And to back this out the other way, to get like 213 in binary, you start subtracting. So subtract the biggest number that goes into it, put a 1 there. So does 128 fit into this? Yes. So 212 minus 128. Now you have 84. Does 64 fit into that? Yes. So then you subtract 64 out of there, and so on. And you just keep working. Can you subtract 20 out of, or can you subtract 32 out of 20? No, you can't. So 0 goes there. Can you subtract 16 out of it? Yes, you can. So you can do that to work from decimal back to binary. Not the fastest process.
Gotcha. And then in these 8-bit sequences, you can just go through 0 and 256.
Right. So
yeah.
So here's that. Yeah, good point. So here's the catch. So what happens if all of these are 1s? What value does that come out to? And this is the maximum you can have for an 8-bit value because we have 8 bits right there.
Yeah.
What was your answer?
I thought it was 256, but let's see what the calculator says. Or 0 to 255. Yeah.
So that's the catch.
Yeah.
So 8 bits here comes out to 255. One of the easy things you can do in your head to know if it's an even or an odd value is if the 1 bit's flipped, it's an odd value. It can't be even.
Right.
So 0 to 255 is the highest you can get with 8 bits here.
Yeah.
So yeah, that's the maximum range of an 8-bit value. You did something interesting there that I was going to touch on later, but I can just touch on it now. So did you notice what happens as soon as we got to 256?
Oh, it just adds another one? Or,
Yeah.
Yeah.
So what we ended up with was, instead of an 8-bit value, we now have a 9-bit value. And so we have 256. So you can keep extending this table out. So 256 is the 9th bit. 512 is the next bit after that. Just keep multiplying. And that's where you get 1024 and so on. So you're not limited to just 8 bits if you're computing in 16 bits or 32 bits or 64 bits. You just keep going with this scale. And the same rules apply. So what just happened here was also a little bit of binary addition. So if we have, let's just do a bunch of zeros again. And let's put this table above it. Okay, so we've got a 0. If we add 1 to this, so this is just if we were, let's do something else here. Let's do a decimal base 10 example just to drive this point home. So 6 plus 1, right? 7. Then let's go 9 plus 2. And then, so how do we do this one? So 9, we have a 10. So we carry a 1 over here. So we know we've got a 1. And then we have 1 left over. So I got another 1, right? Same thing applies to binary. You just do your carry earlier. So this is how you do math in different bases. So binary, so we just did base 10 decimal like we're used to counting with. Binary is base 2. So anytime you get to 2 instead of 10, you carry. So if we were to add 1, we'll just take these off for a second. So if we were to add 1, we're okay. We can, let's do this line here. So we're adding these together. Oops. So we have a 0 plus a 1, that's a 1. We have a, so now we've got 1 up here. Let's add another 1. So a 1 plus a 1 is a 2. We can't have a 2, so carry the 1 over here, and we have a 0. And then so now if we have 1, 0, and we're adding 1, well, we have a 1 here, so that's a 1. We have a 1 here, that's a 1. Now if we got 1, 1, and we add 1, 1 and 1, that's a 2, so we got to carry that up here. So that's a 0. We carried 1 over here, so that's a 2. So that's a 0, and we got to carry it over here. And so Now we got that. So a 1, 1 plus a 1 carries over to here, and really what this is 3. So 2 plus 1 is a 3, plus 1 is 4, and so now we got 4. So still just simple addition, you just do the carry sooner.
Yeah.
And that's what's going on with binary under the hood there. So anyway, with all that little background there, let's jump back to this part, because there's a bug in this code right now. Any questions with what we've got up until now?
Nope. That's frankly like a much nicer representation of the sort of like translation between decimal and binary than I've found elsewhere. Like as far as simplification goes. So yeah.
You'll hear a lot of different things out there, and I think my quickest advice for binary to decimal is that's how you do it if you have to do it, but try to get out of doing it as soon as possible. Decimal to binary is not a pleasant conversion in programming. It can be better to represent your data in either binary or hex, and we'll get into that in a little bit here. There's a bug in our program though right now, and that's if the status is 0 or 4 or 8, we're going to return OK, but otherwise we're going to return an error. But we don't care about bit 2 or 3. So what we've got right now is that if it's 4 or it's 8, so if either of these two bits are set, we're okay. But what happens if, I think this is physically impossible on this sensor, but what happens if both of these are set? So now we've got a 12. And so if I enter 12, it says, hey, we've got an error. But really that just means, well, no, it's the 2 bits we don't care about. So the bug in here is now we've got to do or status equals 12. And now that's fixed. And so the more bits that we want to flip that we don't care about, the bigger this logic statement grows. So that starts getting really inconvenient. Plus what we just went through, it's really hard to tell when you're looking at this binary table of like, hey, I care about this bit and this bit. It's really hard to see those bits when we're in decimal here. So let's flip this over to another way of representing this. Let's start by writing out the bits, actually. I got to remember how to do this in Elixir, but I think we can do 0B. And I think we can write the bits out like this. Let's just see if it lets us use this as a value. It does, okay. So let's just write our values out like this to start making this easier to read. So 3rd bit, 4th bit, that one, or either of those. And so now we can say, do we have a 0? Do we have a 4? That's still okay. Do we have a 5? Now we have a problem. I can take these values in too, and that's still working. And so do I have that bit set? That's an error. So we can start looking at this closer to the way that we get it from the sensor, closer to the way that the program is thinking, closer to the way that we're actually manipulating these bits rather than that decimal value. But this can get a little hard to read what value is what. Like this kind of starts blurring together. Actually, no, wait, I take this back. There's another way to go about this first. let's get rid of this whole status blob first, and let's start thinking through this in terms of bits we do and don't care about. So 3 and 4 here are our don't care bits. And can we do something that helps us get rid of this mess of statements here? And to do that, we're going to go to the Elixir bitwise operations. And if I bring this up over here, we have ways that we can perform calculations on bits similar to how we could perform them on numbers, except we're thinking now in individual bits instead of, also in the math we're used to thinking about. I go about this a different way. We just did the addition example. So we're used to things like addition, subtraction, multiplication, division, the 4 basic functions, things like that. When we start looking at individual bits, we have another set of operations that we can start using. We have some of the things that you see right here. We have and or, and XOR, and not, or inverting. And those are things that can help us work with bits. And what each of those types of operations do, let me just list some of those out. So we have and, we have or, we have XOR, we have not. Those are going to be some of the common ones. This is going to be inverting. So if we were to look at this and say, I'm just going to do 4 bits here. And you were to run these through a not operation, it's going to flip each of those bits. So if we have 1010, it's going to become 101. Sorry, I said that backwards, but yes, 0101 becomes 1010, right? So anything that's a 1 becomes a 0, anything that's a 0 becomes a 1. And is going to be anything that, anytime there are 2 1s, so let's just say 110. Anytime there are 2 1s, we get a 1. Anytime there's a 0, the 0 is the dominant number, and the result becomes a 0. So a 0 and a 0, we get 0. A 0 and a 1, we get a 0. A 1 and a 1, we get a 1. And a 1 and a 0, we get a 0. Or is kind of like the opposite of an and. So anytime there's a 1, the 1 is the dominant digit, and you get a 1 out. So here, 0 and 0, we don't have a 1, so we get a 0. 0 and 1, we do have a 1, so we get a 1. 1 and a 1, we get a 1. And a 1 and a 0, we get a 1. And then XOR is kind of like the combination. It's kind of like the combination between an and an or. It's if any 2 digits are the same, you get, I think it was the opposite of that digit. Or no, sorry, if any 2 are the same, you get a 0. If they're different, you get a 1. So a 0 and a 0, those are the same, you get a 1. 1 and a 0 are hang on, I feel like I'm messing this up now. This is the one you don't have to use too often in practice, but it's used in cryptography and checksums and things like that. So let's just double check this. 0011. That's 0B. Oh, DXOR. There we go. All right, so we got a 5. So this is 101. Yeah, okay. So anytime the digits are the same, you get a 0. Anytime the digits are different, you get a 1. So this was like OR, except a 1 and a 1 cancel each other out, and you get a 0. and and or and a little bit of not, but and or are probably the most frequently used ones. Like you see us doing or down here in operations all the time. And is the one that we're really going to focus on because and lets us build masks, bit masks. And so what we'll do here for 3 and 4 are the bits that we care about or don't care about in this case. We can use that to build a mask of either what we care about or what we don't. So let's say we do care about this. Let me back up and say we'll care in this case if we want to send an error. If we don't care about those bits, we'll send them through as an OK value. So we'll say, do we care about bit 8 as an error? Yes. We care if 7 is an error, 6 counts as an error, 5 counts as an error. 4 doesn't, 3 doesn't, 2 doesn't, 1 does. We now have a mask. And I can say this is 0B, whatever. So now if we import bitwise here, we can, or actually here, let's start running things through this mask before we go to code. So now let's take something that we don't care about here. And if we and these together, so even though we have one bit flipped in this table, if we apply the mask to this value that we have here, we do care about this bit, but it's a 0, so we get a 0. We do care about this, but it's a 0, so we get a 0, and so on. We have a 1 here, so there's something in that value, but in our mask, we say we don't care about it. So this is a 0. We don't care about this bit, so it's a 0. We do care about this, but there's nothing there, so 0, 0. So we end up with a status of 0 when we AND this. So even though we had a value here that could have been considered an error value when we apply this bit mask and AND it to the value, we end up with a 0 coming out, and that status looks like it's okay. If we took this again and had, let's just say we do have this flag set, and let's say we have another one set over here that is one of the bits that we care about, then we end up with 0s. But now here we have a 1 in the value, and our mask says, yes, we do care about this bit. So now we get a 1 that comes out of there. And so now we do have an error code of 1. And then we can throw an error based on that. So going through that, there are 2 ways you can write logical AND. In non-Elixir languages, usually it's just a single ampersand. In Elixir, you import bitwise and it's 3 ampersands because the single ampersand means something else in Elixir, so you couldn't use that. And in the guard statements, for some reason, you can't use these operators in the guard statements when you have a when clause here. So we're going to use the long name for it, which is binary AND. And so we're going to AND the status with, at this point, not a 0. We're going to AND it with our bit mask. So we're going to say we care about those 4 bits. We don't care about these 2, so 0s, and we do care about these. And now we don't need any of those statements there. So now if we go back and run this code, so let's see what just happened. Interesting. That shouldn't have done that. That also doesn't think it's okay. That should be correct. Let's do a little troubleshooting over here. So let's see what happens if we put a 0 in here. It does come out as 0.
Does your band status need to compare against something in the guard?
It should be pulling in the status here, which I said is 0, and it should be comparing it against this value. So it should have
But
been.
does it need to hit a Boolean?
Yes,
Yeah.
sorry. Yeah. So like this should equal 0. You're right. Although, it's the opposite of that. Okay, this was a truthy, not truthy type thing that came out of this. Just to know this, so this came out as a 0. So now in Elixir, though, I could have sworn that 0 is not false. Yeah, 0 is its own thing. So I'm not sure exactly why I didn't take that, but long story short, yeah, we can throw a comparison in there. In a language like C, don't get me started on JavaScript's numbering system. But in a language like C, usually 0 means success. So you could pass something like 0 straight through and it would be okay with it. Yeah, in Elixir, just making the comparison explicit there. Yeah, I should do this.
Yeah.
So yeah, now we've got an okay for that. 4 is okay. And if I were to just start writing these as the binary digits that they actually are, now we can have like 1100 and it's okay. But as soon as we flip one of those bits that we care about, now that we have an error, now we've got an error down there. Any questions so far?
No, I think getting the breakdown on binary and the bit mask makes sense at this point. Yeah.
Cool. The other way to do this, just to throw this out here, I did the inversion here by hand. I'll just put this in as a, I guess we'll just put 4 back in here. Oh. There we go. So I inverted this by hand just to simplify writing it. But we do have B naught. So if we wanted to have this the right way around and say we do care about, or say, so 1, 2, 3, 4, don't care, do care. So instead of saying which bits we care about as ones, we're saying the bits we don't care about as ones are ones. We can invert that and then and it, and we end up with the same thing.
Mm-hmm.
So I did the inversion in my head and just wrote it out here, which is typically how you'll see the masks written. You'll usually see them written as ones for the bits that you do care about. But just to throw it out there, this is one of those cases where like a not could help you out. There's some other things like that. I wouldn't necessarily put a not here in my code by default. But if you need to see what it's like flipped, this is one of those things you can do. Or if there was some reason in your code where you had explicitly like don't care bits and this type of thing were some explicit variable name, then it might make sense to say your mask is the inversion of your don't care bits, something like that. That could make sense. It doesn't come up too much from what I've typically seen, but just to throw it out there, that's one of the places where not can be either handy or where you're doing it mentally and you might just not realize it. So we end up with another problem here at this point, and this kind of thing starts getting difficult to read and understand, and it's not very concise, and you kind of lose your place on which bits are which. Things just start blending together into this stream of ones or stream of the same characters, and it's kind of hard to tell here. Wait, which bit's this one? Once you start getting into the middle of that string. So this is where hex comes into play, because it's like you can think of hex as an easier way to write binary. And so what hex is doing is looking at groups of 4 digits. Or actually, let me put it this way. So if we were to write this in hex first, just to give an example. Wait, we're missing a digit here. Yeah, I think we dropped a 0. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, we dropped a 0. So to write this in hex, we could represent this as F3. And now we just saved a whole lot of space. But if you're just looking at this and don't understand how to decipher it, F3 at first might look even more cryptic than seeing the bits. But the catch is being able to see this in your head. So to break down hex, hex is looking at binary in 4-bit groupings. I should probably also back up and say hex is a base 16 counting system, digit system. I forget the mathematical term for it. But we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And remember, as we were talking through base 10 and binary earlier, in decimal, 10 is, don't think of 10 as 10, think of it as 9 carry a 1. Right? So we have 1 tens of something and 0 ones of something. That's going to become important in a second, because in hex we don't have 10 as we think of 10 in decimal. So we have 16 different digits that we can use. So we've got then A, B, C, D, E, and F. And so we've got 0, if we were to look at this in decimal. Oh, that's going to be really hard to type like that. I'm just going to type the ones that are different. So in decimal, this would be decimal 10, decimal 11, decimal 12, 13, 14, 15. So in decimal, we would have 16. In hex, we have, back to addition here, we have F plus 1. What happened in binary when we had this and tried to add a 1 to it? Right? We carried the 1. So same thing in hex. Carry the 1. We have 1 16 of something and 0 ones or 16ths or whatever you would call it of it. So in hex, 1 0 is decimal 16. But again, like I was saying earlier, throw decimal away. It's really hard to think of. It's really hard to do conversions with it. What we really care about is thinking in binary. Binary is how the computer thinks. So ignore the decimal for now. Know that we've got 0 through F. That's 0 through 15. This is the part to remember in your head. And really 0 through 15 are the largest amount of decimals you probably need to practically remember in your head. But the other conversion for this now, I'm actually just going to get rid of those columns, and that's going to be a little bit of a pain. Hang on, I might have to rewrite this here just to make it easier. Okay. What we're actually going to do is look at this in binary. Hex and binary convert very nicely between each other, and hex makes binary easier to think about. And it makes binary more concise. So each one of these hex digits, if we were to convert, oh, you can convert all this to decimal. I'm going to get off that track. If we were to look at this in groups of 4 bits, a 0 is 4 bits, 4 zeros. A 1, we know what a 1 looks like. 2, I'll put the decimal conversions back up here just to make it easier for folks following along right now. If there's a 1 in this column, it's an 8. If there's a 1 in this column, you add 4, add 2, whatever. So that's a 1. I'm going to blaze through a handful of these here. So that's a 2. 0, 0, 1, 1. So 4. These 16 patterns are the things to memorize. And like you saw, even if you start getting rusty on some of them, if you remember this bit up here, it's not too hard to reverse engineer them in your head if you have to think about it for a second. Because you can think about it of an A. Okay, that's supposed to be a 10. I need an 8 plus a 2 to get to 10. So, 1, 0, 1, 1. I need an 8. I don't need a 4. I do need a 2. I don't need a 1. If you've got these 16 patterns in your head, you can start seeing these patterns in larger strings of binary, larger groupings of binary, and be able to convert them back and forth mentally. So you can start taking things like this and saying, oh, let's just take the first one. Oh, and the other thing, going back to the decimal table, is 0 through 9 are the same in both decimal and hex. So you only have to start thinking about the difference between the two in the first digit when you roll past 10 in decimal. So then you go to A through F. So if I have something like this that's a 4, that's something that becomes pretty easy in hex because it's also a 4. So we have 0x something and 4. So, and we've got 4 zeros here, so that's a 0. So just let me consolidate these easier so it's easier to see the groupings here. So hex digit here is 0. This is a 4, so this hex digit is 4. If we grab another pattern, like the 12, this is still a 0. This is not a 4. This is an 8 plus a 4, or a 1, 1, 0, 0. So we've got 1, 1, 0, 0. That's a C, which is also a 12 in decimal. So this becomes hex 0C for this grouping of bits. So now if we build up our mask, I'm not even going to do our mask in decimal because we kind of don't care about it. We're just going to take this value here. We're going to split it into groups of 4. That's not groups of 4. We're going to split it into groups of 4. And so what digit is the first group of 4?
F.
Yep. And F is easy to remember because it's just a bunch of 1s. And then what digit is the second group of 4?
3.
Yep. So we can take that value there and reduce it to 0xf3 and get rid of this. And now we have a really concise piece of code that says, here are the bits that I care about. And you can work this backwards too. We've kind of got that here to cheat a little bit, but if we were thinking about F3, mentally, you say F, okay, well, that's 4 ones, and then I have a 3, so 0, 0, 1, 1. And so now you can see that pattern of bits either in your head or you can jot it down a lot quicker. And if you're looking back at your data sheet and you're seeing one, do care, do care, do care, don't care, don't care, you can work this backwards and say, okay, now that I just reversed that, which bits don't I care about? Okay, 1, 2, I don't care about these, skip 2, okay, here's the 2 I don't care about. So you can start doing that translation a whole lot faster. And this is something where you can have a little table like this to cheat with to start with. Since this is only 16 values, this gets pretty quick to memorize when you use it in practice. And again, sometimes you happen to forget some of the ones in the middle, or like they come to you a little slower. So that's the time where, as long as you know the fallback to decimal here, and you're going, oh, wait a second, what's a 1100 as I'm staring at? I'll just put that down here. What's a 1100 as I'm staring at this? Well, I have an 8 and I have a 4 and I don't have anything else. So 8, 9, 10, 11, 12. Okay, that's a 12. Or you can go 8, 9A, B, C. You can count it like that too. No, okay, I got a C. And you can do those small conversions a lot more simpler than you can trying to think about these big groupings of digits. So like the whole advantage of hex is it lets you think about binary and about bytes or bits specifically in groups of 4 bits. You only have to keep 4 bits in your head at a time. And so now that we got this, let me just turn this, let's turn this into code comments, and then let's just delete the rest of the stuff down here and run the code again. So now 0 is valid, 4 is still valid, 5 should be invalid. But now we can also start thinking in hex. So this code right here is running right now with anding 0xf3. So what would happen if, let's just start doing some conversions here and say we've got, let's get something back from the sensor and say, you know what, we've got some drift and we're still in preheating. So we'll do 0, 1, and then a 1 at the end. So we'll do that. So what does this value come out as? Well, actually, first of all, we can say 0, 1, 0, 0, 0, 0, 0, 1, and we can put that in, and that's invalid. Oh, sorry, I was supposed to put that in as binary, not hex. Hex would also be invalid here, but that's a much bigger number. So, okay, our binary is invalid, but what does this come out to in hex to be able to think about this easier? And just kind of walk through how you're breaking it down now. You can just talk through this out loud.
Yeah, I mean, splitting it into 2 parts, you got 0, 1, 0, 0, and then 0, 0, 0, 1.
Mm-hmm.
So we know 0, 0, 0, 1 is 1.
Yep.
0, 1, 0, 0, 0. Yeah, I'm just looking at the table. That's 4.
Yep. So we put 4, 1 in here, and sure enough, invalid.
Yeah.
Let's grab something else, and let's say we've got, let's Let's say we've got that. What does that come out to?
Yes, it's 0 and 8.
Yep. And that's okay.
Yeah.
And this brings up another good example here, because this is, so what's the difference if we've got 0, 8? What's the difference between these two values?
The number of bits.
Yeah, so that's the big thing. Mathematically, they're equivalent. But the really important piece of information here is that the 0 says we care about an 8-bit value. We have 4 bits here and 4 bits here. This one says we care about a 4-bit value.
Yeah.
And so this is the thing that like a compiler won't catch you on. Both of them, the math will come out the same, but the information you're conveying to another developer can be really important between this and this, because if we were dealing, this says we're dealing with an 8-bit value or 1 byte. If we were dealing with a 16-bit value, we could write it like this and say we've got 1 byte here. That byte just happens to be 0, but we care about that byte, or it's conceptually important, and we have another byte here. So that's 16 bits in total. And so that can be why it's important to pad your hex or your binary values if you're writing binary values, but you typically don't write those too much. Padding this can convey that meaning of how many bits are either you working with or how many are important. And I think this just takes us through all of the binary stuff, or the bitwise operations here, just to put this back up on the screen. The bitwise functions here, we didn't talk about bit shifting, but that could be for another day. I could briefly explain that. But yeah, so we've got the convenience functions here that are easier ways to write the other things that I talked about. So triple ampersand is and. We'll get to bit shifting in a second. Or should be triple pipe usually. Yeah, here it is, triple pipe. So that's or. Not or inverting is triple tilde. And again, if you're using a language like C, you only use one of these symbols. Elixir just had to do it because the single version of this has been stepped on for other language features. And then the other thing we didn't touch that I'll just touch on very quickly, so that it's known that it's out there, but it doesn't really apply to our specific example of what we were doing today, are the bit shifting, shifting left, shifting right, which is either this operator here or in other languages, again, just this single left to right arrow usually. Or they've got BSL and BSR for the longer hand form of writing it out. And what those will do is let us take, let's just say, let's get rid of all this for a second. And let's put some zeros here. I'm going to do this with 4 bits so it's easier. So if we shift this to the right one, it's going to do exactly what it says. This 1 moves over 1, or sorry, moving to the left. It moves to the left 1, and if there was nothing before it, that empty slot always gets padded with a 0. And same thing for the other direction. If we were to shift this to the right, then that 1 is going to roll off, and this gets padded with a 0. This can be one of those handy things where what happens if we needed these 2 bits? Maybe I'll just go into this quickly. what if we needed these 2 bits and needed them to, we need to operate them on them lower down here where they're easier to work with. And really this, in practice, this would be the thing of where if you're dealing with, say, like a 32-bit value, these bits are way over here on the left somewhere, and you want to get them into a easier to work with 8-bit value for something that you're doing. You can take these bits over here and say, so we're working with like 1100. Let's shift them over 2 places. So now the bits that we care about end up right here in the lower side of that bit. Now we can do things like say let's and our don't care bits here, and now we're limited to 3 values that this could come out to. So we don't have to worry about like, is it an 8, is it a 4, is it a 12? This is it's a 0, it's a 1, it's a 2, or it's a 3. You know, there are only 3 possibilities down here. The thing I didn't say is we would and this with don't care, don't care, do care, do care. So like that type of thing. So we can only work with these 2 bits. They're now limited to only being number 1 and number 2. This starts making this a whole lot simpler. And we're working with it in a whole lot lower number space now. The other thing that we could do with this is maybe we need to put something else down here now. So we've done something with these digits. We'll just say that they're 0011 still. Let's shift them back over now that we've worked with them. So shift them back over 2. And now let's say we've got some other value that we want to put in here. So, you know, something else that we have in this space. So let's just say like it's a 0001. Well, now we could AND these together, and now I've got a 1101. And so now we've encoded 2 different pieces of data into these 4 bits. And really, you can see how this can stretch out into being 8 bits or 16 bits or 32 bits. So we have one piece of do care data right here that means one thing. These are now a completely separate meaning, but we were able to pack them into a smaller memory space. Like a sensor that doesn't have a whole lot of memory and needs to have different meanings over a lot of different bits. So this isn't the kind of stuff you typically do up in an Elixir application for like thinking through your application. You'd be breaking these out into variables, and you'd break these things out into stuff that has its own meaning and things like that. But when you're trying to get data like into and out of a sensor or some really resource constrained device, this is how you can be building up those bitmaps where those different bits or those different groupings of bits can mean different things. And you can encode and decode that data to be able to get into and out of your application. The other thing that's kind of like a cheat for shifting that's interesting to know about is if we just take, let's just take a binary 1 here, and oops. And if I start shifting it over, look what happens at the base 10 value here, which might be a little hard to see on the screen, but I don't think I can blow the calculator up. So binary 1 comes out to a decimal 1. If we bit shift that over 1 place, now it's a 2. If we bit shift it again, actually, wait a second, I might be able to do this in decimal. Yeah, okay, so this is gonna make it easier to read. So now it's a 2. So now let's bit shift that over 1 more place, and now it's a 4. And shift it over 1 more, and now it's an 8. So this bit shifting is a binary trick you can do to multiply a number by 2 by itself. It's a way to do powers. So shifting one over just did, 8 times 2. Shifting it back, so this is where my mental math starts failing because, um, so shifting over 2 is like cubing it. So 4 with a bit shift of 2 is like 4 squared, right? And a bit shift of 3, I think, cubes and so on. So if you need to do like that multiplication style stuff, where you're doing powers of things, bit shifting can do powers that are compatible with the binary system, if that makes sense. It has to fall into what binary likes to do, but you can get those calculations kind of for free by bit shifting. And again, this is probably more like microcontroller tricks and stuff like that up in an application like embedded Linux application and stuff like that on an application processor and a higher powered processor. This is going to be harder to read in the code and really one of those tricks to save processor cycles and things like that than it is for code readability. But if you see bit shifting happening like that and it seems to be numerical, it could be because you're trying to get a power or a what would be like square root or something like that of the thing. I think that runs us through everything. Any other questions?
Just a couple more unrelated to this, but on the data sheet, I was just gonna get, since we're using the data sheet as an example here. So in the where it says DF3, it says like status bit.
Mm-hmm.
Is the table below referring to DF3?
Yes.
And it's
that's what it looks
a
like.
Status bit, but it's a byte, I guess, or is that typical, like how you would describe that, even though it's 8 bits?
Oh, wait a second. Actually, I'll say this is a data sheet that's newer to me. I'm not as familiar with this one. The other thing to throw it out there is this data sheet, I'll just say, did not originate from the US. It originated from overseas. So one of the catches to that is there could be translation errors in the data sheet that you have to take into consideration.
Yeah.
So I think when they say DF3 status bit, seeing one of the command and response examples down here,
oh, I see. Yeah,
where they have these groupings, it looks like each one of these is a byte, not a bit. So I think they meant DF3 status byte, and these are the 8 bits in that byte.
Gotcha. Okay, that helps me make a little more sense of this, and then how everything's converting. So, okay.
Yeah, and this is something that you can see in a data sheet too, where like maybe these 2 bytes are a status register. And so instead of just seeing one table here, you'd see 2, and so you'd see like bits 0 through 7, and then you'd see 8 through 15. And so you've got a 16-bit register you're working with for those status bits.
Yeah.
So they could break these up in a lot of different ways. But like in this one, you can see bit 7 is reserved. So this one isn't even being used.
Okay. I think I'm good for now.
Cool. Anything else?
Nah. Thank
All
you
right.
for like the tutorial there, though. Like that's actually, you were not over promising when you said you had um a relatively high impact breakdown. So yeah, I appreciate it.